Yeah, thank you. So the IFORS stands for the International Federation of Operational Research Societies. It was founded in 1959 by three founding national societies, one of the UK, the USA, and France. So now, after 66 years, we have a global family of 55 national societies, which together includes over 30,000 individual members. So the goal of IFORS is to promote the development of operations research worldwide, both in methodology and practice, and also to encourage interchange and collaborations among the members. And because we now have 55 national societies, IFORS is divided into four regions. ALIO, which includes Latin America, and APORS, the Asia Pacific region, European societies, and NORAM, North American societies, which consists of Canadian Society and IFORS, the USA National Society. So we advance our mission through a number of initiatives. So the most prominent may be our conferences held once every 3 years, and just want to advertise the next one will be next year in Vienna. We also have two flagship journals, one being International Transactions in Operational Research that's been ongoing for a couple of decades. And of course, we have two speakers who won the Best Paper Award in this journal. Another is a newer journal that we have recently started, Sustainable Analytics and Modeling. And I encourage you all to submit papers to that. So as I mentioned, we have a Best Paper Awards for ITOR, and we have global webinars. This time we are featuring the best papers, but we have global webinars periodically every 2 or 3 months on various topics. We also have our website and a newsletter, and we sponsor distinguished lecturers at major regional conferences. We also support young researchers through supporting their attendance at summer and winter schools held by the different regions. And we're also making a big push to support new OR societies, especially in developing countries. The IFORS is run by an administrative committee that consists of vice presidents for all the 4 regions, together with our president, who currently is Professor Hector Cancela in Uruguay. He is now currently the president also of his university in Uruguay. Okay, so as advertised, I want to invite everyone to consider participating at our next triennial conference in 2026, which we held in beautiful Vienna. It looks to be a fantastic conference, and I really encourage all of you to consider to participate. Next. Okay, and again, we have 2 publications. I mentioned ITOR and Sustainability Analytics and Modeling. Our publication is overseen by one of our vice presidents, Professor Greet Vandenberg. Next thing is we have our website. We also have a newsletter, which issue every 3 months, and it features and reports of activities all around the world. And you can subscribe by clicking on by going to our website, www.ifors.org, and clicking on the newsletter site. So I think the next one coming out soon. Okay. We also have a social media presence, which will bring up news much more frequently. We have our LinkedIn page, and I encourage all of you to follow that. Okay, so another thing is our global webinars. Like I said, we started this during COVID times, and we've been holding this periodically, and you can take a look at all previous global webinars from our website and watch everything that we have been speaking about in past global webinars. Okay, so today's webinar features 2 winners of the ITOR Best Paper Award from 2024, and they are, drum roll, Professor Stefano Novellani from the University of Pisa, who will talk about exact models for the flying sidekick traveling salesman problem, and Professor Christian Leonardo Camacho Villalon, I probably mispronounced it, who has worked in many different places and is now in Slovenia. Okay, so we will start off with Professor Novellani. I'll just give a brief bio. Professor Novellani is an assistant professor of operations research at the University of Pisa. He holds a PhD in automatic control systems and operations research from the University of Bologna. and also degrees in industrial engineering from the University of Modena and Reggio Emilia. This research is focused on combinatorial optimization, meta-heuristics, stochastic programming, and applications to real-world problems in vehicle routing, last-mile delivery, shared mobility, and sustainable logistics. He has also traveled the world, having studied in different places, and also recently returned from, I guess, a postdoc position in Chile. Okay, so without further ado, let me hand over the floor to Stefano.
Hello, everybody. Stefano Vellani here. Today I'm going to present this work that we published on International Transaction and Operation Research called Exact Models for the Flying Sidekick Traveling Salesman Problem, which we published together with my colleagues Mauro Dell'Amico and Roberto Montemar. So the problem works on drones. The idea is to use drones to make deliveries. So first of all, let me give you a brief introduction about drones, or as they are also called, unmanned aerial vehicles. They are increasing being more and more relevant, especially in the civil domains, which is the one that I'm interested in today. Some examples: precision agriculture, disaster and emergency management like wood fires, floods, logistic operation. Why are they so? What are the advantages of drones in these systems? Well, normally they are cheap, they are fast, they can reach places that other means cannot reach, like for lack of infrastructure or for other reasons. And again, they have no humans on board. Some application of drones, which I think might be interesting for the audience, can be divided into two categories. One is the use of drones for data and information collection, that may list some environmental monitoring, inspection, like in construction site, mapping, surveillance. And the other category is good transportation. I'm talking about parcel deliveries, medical and food delivery. So the different thing is that in one of the two categories, you need to move things, and in the other, you just collect information. I will focus on the second one. I mean, the one talking about goods transportation. But let me tell you something which I think might be interesting. The two categories lead to two different modeling perspectives. Data information collection normally are used to maximize coverage. And the constraints might be the battery life of the drone, some data resolution requirement, environmental factors might be important, like wind obstacles. And we have no payload constraint because we have no things to bring somewhere. And then means that the modeling type resembles coverage, path definition, and synchronization is not, with other things, is not important. While on the other side, and good transportation, synchronization is important because we want to synchronize drones with different vehicles and its base station. The objective can be to minimize delivery time, distance, costs, and the battery life and drone payload are interesting in our models. And here, if we want to talk about the modeling type, we move close to vehicle routing problems with some pinch of scheduling and in it. So two different categories, two different modeling type. As I said before, I focus on the last mile delivery with drones. So a small comment on e-commerce. As we all know, e-commerce has been booming in the last few years. Here you can see a report from Statista that says that in the last decade, the number of the billions of dollars in e-commerce sales have been increasing steadily, linearly, I would say. And in the next few years, it is expected to be the same. So many parcels need to be delivered, and to do so, we should research on different ways of doing it. A report from McKinsey says that customers are willing to pay more for same-day delivery and even more for instant delivery, and they expect, with a maybe optimistic forecast, that autonomous vehicles will deliver 80% of the parcels within the next years. Not just drones, also other autonomous vehicles. But that's the point. I mean, many deliveries, we need to look for other ways that are not just the classical vehicles. One of those are, for example, the use of ground robots. So not just drones, but also ground robots, where I think that in the modeling phase, it would be interesting to see the pedestrian interaction, for example. Then cargo bike should be explored. Paths and lockers and micro hubs should also be explored, when you can mix vehicle routing, facility location decision, and mix all of these together. And I want to suggest the audience to check these two service, one by Albert et al. And the other by Boyson et al., where they explore these topics with an operation and research perspective. Now, the growing demand for faster deliveries has motivated companies to explore the use of aerial vehicles for deliveries. We have here a list, just a few of them, like Amazon Prime Air, experimented drone delivery. Then we have Zipline, which focus on medical and pharmaceutical supplies in Africa. Then you have Wing, which has done drone deliveries with Walmart, a collaboration between Flytrex and Uber Eats. Then DHL in Germany, JD in China. So we have many, 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 many more. In particular, in this presentation, I will be talking about one problem, which is called the flying sidekick traveling salesman problem. That has been first defined by Mari and Chu in 2015, yes. And it refers more or less to this system, which was, it's by UPS. It's called Horsefly System, done in partnership with Workhorse Group. Well, we have a truck, and the truck can do the classical deliveries, but then on the truck, is installed a drone. And so the drone can actually leave the truck, serve a customer, and come back to the truck. In order to allow a parallel deliveries and decrease the completion time and finish the deliveries earlier. And also here I wanted to put some other system, which is called DJI Dock 3, when you can actually buy a dock and put it on your pickup and do the same thing, but with a pickup instead of a truck. But anyway, talking about the problem, the Flying Sidekick TSP, again, was introduced by Mari and Chu and in 2015. And here we have one truck that can leave the depot, visit some customers and come back to the depot. And at some customer nodes, the drone can leave the truck, serve a customer, and come back to the truck in another point. This triplet of nodes, launch, serve, and return, is called a sortie. And the idea again is that we can do this within the battery endurance, so the drone cannot fly forever. And we want to minimize the completion time and service all the customers. Some foundational work, one by Marici again, which the first defined the problem and proposed a 3-index mixed integer linear programming formulation. They proposed heuristic and exact formulation. The exact couldn't solve with up to 10 customers instances that they proposed. Then we have from the work by Agas et al. They defined a similar problem where loops were allowed. So loop is where a drone can leave the customer node, service a customer, and then come back to the same point. The endurance was infinite, and then they had multiple. The truck could visit the same node multiple times if it was convenient for the drone. They could solve instances with up to 10 customers. Bowman solved the same problem with dynamic programming, and instances that could be solved with up to 15 customers. Then just an idea of what happened in the meanwhile, people were working also on meta heuristic here. I just want to mention the high talent, the Freitas Penner, which published many papers on heuristic for this problem. Here, this is not the topic of my presentation right now. So I come back to the exact method. One is by Poikon et al. They propose a branch and bound for this problem with loops, solving instances with up to 9 customers. Eureka Osmoto proposed the composition method, solving instances with up to 12 customers. And us, with our colleagues, we propose also a previous paper where we propose different formulations. Here, we first define the fact that the drone can wait hovering or not hovering for the truck. So the idea is that at some point, the truck and the drone must meet and then start their routes together again. And so in one case, the truck can wait for the drone, and that's okay. But then the other case, when the drone waits for the truck, we should decide, is the drone waiting without consuming battery, which can be represent the fact that the drone waits on the ground, or is it hovering and then we are consuming the battery? The two models are slightly different, and the problems are also slightly different. In such a paper, we saw recency with up to 13 customers. Then, while we were developing our paper, actually, there were two other research groups that are working on the same thing, and then I want to mention my colleagues. One paper is by Roberti and Ruth Meyer. They propose exact solution for TSP with no loops, no endurance constraint, and single visits. And they propose a compact milk formulation and a branch and price. They could solve easily with up to 9 customers with a milk formulation, and the branch and price could solve larger instances. Actually, our idea here is to produce compact formulation, so we wanted to show the difference between what a difference like compare with respect to the milk formulation, but of course the branch and price solves larger instances. And then they can also incorporate variants such as a loop and a different value of endurance. The second paper of researchers that were working on the same topic together in parallel with us was by Sherman et al. When they proposed milk formulation and branching algorithms with the same problem with loops, limited endurance, single visits, and the drone waiting on the ground without flying. They could solve easily with up to 14 customers and few with up to 20 customers. Now, since these publications, some other works have been published. So let me mention the work by Boccia, Mancuso, Masone, and Sterle, which improve upon the literature. And also another thing I want to mention is that, of course, we can increase the number of drones, not just one truck and one drone, and we can make that model different. So in the following years, people have been working on different and harder, let's say, problems. And one I think it's interesting is to use more sophisticated energy consumption function, because in the model I'm talking about, we have a consumption function of minutes. What I mean is that the drone can fly with up to, 40 minutes, and that's how we consider endurance. But one could consider endurance in a way more sophisticated way, like including, the weight of the drone, the speed, and also nonlinear functions. So I suggest researchers to go also in that direction. The last thing about literature review, again, other people have been working on the mixture between drones, lockers, trucks, and other stuff. So another research topic I think it's interesting to explore is that direction. But let me come back to these exact methods, and especially compact formulation for the FSTSP. Previous work where I'm not going to talk about all this table, but just to show you that the previous work were solving similar but different problems. So the idea of myself and my colleagues, and also the other two papers I mentioned before, was to find methods that could solve larger instances, but also they could be more general. So that's the idea. Our contribution was we proposed 3 formulations. One with 3 index binary variable for the drone sortie. So a drone sortie is represented with a 3 index binary variable. And then 2 formulations with 2 index binary variables for the drone sortie, one with the branch and cut included. We also adapted those models to several variants. And what we did was to reduce the number of variables, especially the time variables. We reduced the number of integer variables considering the drone. And in such a way, we have included a variable that says when the drone is on the truck or not. And this helps to avoid something that happens in this problem, which is crossing sorties. What is a crossing sortie? What can happen if you relax the problem is that you have a track path, and then you have one sortie leaving the track, and then another sortie, another drone leaving the track before the first drone comes back. That's a crossing sortie, and you want to avoid that. So you can either do with this new variable or in a branch and cut fashion, as we did in one of the 3 formulations. We could solve all of these with up to 14 customers and many with 20 customers. Now, I don't want to go into details here. Just let you know that we have an endurance per each sortie, which is E. Drones can be launched and recovered at depot or customer nodes. We have a launching time, a rendezvous time. Some customers can be served by drones, some others cannot. We may have a different metrics for the truck traveling time and the drone traveling time. And again, we need to make sure that the two vehicles are synchronized. So the first formulation, what it does is to reduce the number of variables, reduce the number of constraints, and enable a more compact formulation. I go into detail. Here where we have the classical track binary variable. So if I visit an arc, this value with a track, this takes value 1, 0 otherwise. And then here we have a variable with 3 indices. One, when I start the sortie, the serving point, and the return node. And this takes value 1 if I do the sortie, 0 otherwise. We have a time marker and a waiting time, a variable that takes into account the waiting time. And again, this new binary variable that includes the considered fact that the drone is on the track in some node or not. The objective function is to minimize the make span. The make span can be separated into several components in order to have obtained stronger lower bounds. The component would be the track travel time, the rendezvous and launch time, and the time where the track waits for the drone. Constraints, we have the classical routing constraints for the track. Here we say that the customer is visited by the track or by the drone. Then the time, if the track travels 1 arc, we need to update the time. If we perform a sortie, we need to update the time for in the nodes that are involved in the sortie. And here the W captures the extra time in case the drone waits for the track. The track waits for the drone. Another thing that to allow feasibility is that we need to have a sortie that travels not more than the endurance. So we need to respect the battery endurance for each flight. And here, the constraints that link the binary variable that says that the drone is on the track and all the other variables. So here, this can take value 1, so the drone is on the track. If the track actually it is in that node, then we can have a sortie leaving a node if the drone is in that node. And here, what we do with this constraint is an update of these variables. So let's say that we have the drone on the track, and then we move from I to J, then J can be on the track, but we must take care of the fact that some sortie can leave and some sortie can return in those two nodes of the arc. Binary domain, and just shortly mention that we have included some polynomial inequalities to strengthen the formulation. And I mean, the idea was to reduce the number of again constraints, to reduce the number of variables, and overall to have a more compact formulation. With the same idea, we moved to a 2-index formulation. Well, the big change is that instead of having a variable that says that defines the entire sortie, I, J, K, we have 2 binary variables, one for the launches and one for the returns. So here we go from n to the 3 number of binary variables to 2 by n to the 2 binary variables. So what we change with this formulation is just these two new variables. We do some pre-processing to reduce those variables, and we update the formulation. Here, the objective function is the same. We just include the new variables here instead of the previous ones, but it's exactly equivalent. The covering constraint and the routing constraint also are equivalent. And for the time constraint, we just need to update the one for the sortie. Here, instead of having 1 constraint, we need 2 constraints, not so. We need to update as well the constraint for the battery endurance with the 2 G variables. And then the novelty here is that since now we have two variables defined in the SRT, we need to be sure that when we leave the track and arrive in a node served by the drone, then an arc should of a SRT should leave that node. So we need to ensure that this coherence between the two variables, let's say. And again, we update all the constraint with the z variable with the new binary variables. They do just the same. And we have some bounds and some polynomial inequalities added to the formulation. Built on this, so we have two formulations, one free index formulation, one two index formulation. Built on upon the last one, we have proposed a third formulation. This formulation has the same variables as the previous one, but we just remove the z variables. What happened here is that we might have a solution with, if we solve the problem without those variables, we might have a solution which is infeasible. What is the infeasibility? Again, the crossing SRT. We can have multiple SRT which are not which are crossing, and this is not feasible for us. So the idea here is that we solve that formulation, and with a lazy constraint, we take the infeasible solution, and when they're infeasible, we eliminate those solutions with a crossing SRT elimination constraint in a branch cut fashion. So again, here we reduce the number of variables, but we increase the number of constraints. So this formulation has the same variables as before, but again, without the z variables. Everything is the same, apart from the fact that we remove all the constraints with the z variables. And since those constraints actually linked the x variables, the arc variables, with the SRT variables, now we need to write those new constraints in order to allow this to happen without the z variables. So this means that if I visit a node, then I can have a drone launch there, and this means that if I can have a return when the track actually is visiting that node. Sorry. But the most interesting part of this formulation, it is this crossing SRT avoidant constraint. Let's imagine that in an integer solution, we find a path from I to L, a track path from I to L. So we have a track that goes from I to L, and in I have a SRT, and in L, I also have another launch. And I am sure that there are no drone arcs returning from I to L. So the two SRTs actually are infeasible. In such a way, we can write this constraint which says this is the track route plus the first SRT plus the second SRT minus the case in which we have a returning SRT between I and L. This shouldn't be feasible. So we need to impose that this number of variables doesn't take this value here. And then we can make it actually a bit stronger by including the tournament constraint here and by including more launches from L to different nodes outside of the path P, but whatever, this is the idea. We avoid that solution in a branch and cut fashion. So again, we have less variable, more constraints, but there is a trade-off. And another thing is that we wanted a new formulation that could solve larger instances, but also that could apply to several variants. We could include in all of the free formulation the SRTs done with loops, which means that the launch node and the retrieve node are the same, unlimited endurance, and drone. The waiting drone on the ground could also be applied to our formulations. From the computational results, we implemented everything in C. We use Gurobi as a solver. We use a single thread. And as initial upper bound, we gave a TSP solution obtained in a heuristic way. And here I also leave you the link to all the available material. So first of all, we use the 36 benchmark instances from Marian Chu, each with 10 customers with 2 different drone endurances, 20 minutes, 40 minutes. And the track times were Manhattan distances and the drone times were Euclidean distances. And the way we published these were the best results in the literature. So all the free formulation could actually improve with the best results in the literature. but between the two formulation with two index the two index formulation were the best one. Sometimes the branch and cut could be faster, but I would say that in average, the compact formulation was better. Then we also thought, why don't we check what happens if we change the endurance? So we change endurance and put the endurance equal to 0, which means a typical TSP solution, and equal to 100, which allowed it to have all possible SRTs. And in such a way, we could find two things. One is that the larger the endurance, the harder to solve the problem. And this might be explained because we have more possibilities to explore. And when it comes to the solution value, we can see that having 20, using drone with 20 minutes endurance, we can improve the TSP solution with up to almost 13%, and with 40 with almost 18%. And then with higher endurances, we have no further improvement. But the point here is that using drones in parallel with track makes sense. Then we took also the 20 customer instances with 20 minutes and 40 minutes endurance given by Mari and Shu. These were hard instances. And here we just tested the two best formulation with, as I said, 20 minutes endurance, 40 minutes endurance. Here you can see that we can solve many instances with a small endurance. As in particular, the branching cut here worked better. But when we increase the endurance, our method actually reached our limit. Well, its limit. Another comment on well, we wanted to test our method and compare them with something with the results from the literature. In particular, we compared with the results by Poicone et al., where they propose they solve the problem with loop, and here they have instances with 9 and 13 customers, and we could solve the one with 9 customers within seconds, and all of the instances with 14 customers. Then we also wanted to compare with the compact formulation by Roberti and Ruth Meyer, and here with the problem with loops, we could solve well, we have better results, especially in small instances, but also with when solving 19 customer instances. Here we can see that we can solve more of them to optimality than the one proposed by Roberti and Ruth Meyer. But when solving another variant with unlimited endurance and no service times, they beated us quite easily, as you can see. So the point is that we have, and our colleagues as well, we could solve larger instances, but it really depends on the variant as well. I think that our method could work quite well with problems with loops. So to conclude, we propose novel formulation for the flying psychic traveling salesman problem. We could solve all of the instances with up to 14 customers and many with 20 customers. Our method could be applied to several variants of the problem, and they are especially effective on variants including loops. And the last thing I want to mention is possible future direction, future and current direction, I would say. First of all, I think it's valid to explore methods that combine different deliveries, like multiple tracks, hubs, lockers, bikes, ground robots, and drones. I think we should explore those problems. I think that in the future, we should take more and more care about time-dependent travel times. It's time to include that in our model every time, accounting for congestion and variable speeds, for example. Also, stochastic information is very important. For example, we have a lot of uncertainty when it comes to the presence of the customer when we do a delivery, and I don't know, like service times as well might be stochastic. And last thing I mentioned again, we should take care about nonlinear energy consumption for drones, including payload, wind, and speed. And also some other objective can be a nice extension. So I leave here all the paper I have mentioned at the end of the presentation, and thank you very much for listening. I'm ready for the questions.
So thank you very much, Stefano. So maybe I'll just start off with a question.
Yeah.
In fact, you've already alluded to it. I was thinking with more realism, we need time-dependent travel times or stochastic travel times, because while the drone travel times would be pretty deterministic, that's why we go to the drones, but the truck travel times may, may in fact face a lot of traffic situations. So how do you anticipate, that what is the level of difficulty that adds, and what are some of your preliminary ideas of how to tackle that problem?
I think it's very hard to solve those problems. As you can see, these problems also, I mean, already including synchronization of different vehicles in these problems can lead to very hard problems. I mean, we struggled with instances with 10 customers at the beginning of this research. And so including also this might be very hard, but I think it's valid and it's time to take that into account. Again, maybe not just with exact methods or maybe with meta heuristic, but I think we should include realism in our models. That's what I meant.
All right, so I think we have a question from Sue Merchant. Thank you, Sue. She's from the practice side. So her question is, how do you convince the companies to use this optimization methodology that maybe they don't understand?
So the optimization methodology, it's true, maybe they don't understand, but I think when you come with the solution to companies, then they will understand that. For example, here, an easy result that we have is that if we include this, if we include just one drone on one track, we can improve the time, the delivery time up to almost 13%. I think that this way they will understand. So one, you can go to practitioners with solutions more than methods, and then methods are behind the solution. I don't know if you agree with that.
No, well, certainly we need convincing data to convince. But I think maybe another side of Sue's question is these drones are also expensive financial investments, right? So for them to, even if you have data to show that it works for another company, how do you convince a new company to make this investment? And I guess related to that, I also have a related question, which is maybe the technology is improving. So now, while you have to pre-program a fixed rendezvous time and place for the drones, maybe in the future that technology can be sort of done on the fly, right? So that involves increased complexity of the problem. And maybe all these, optimization algorithms and the hardware programming will be a continual investment, right? So how do you convince the companies to do that?
Well, I think that with data, it's the only way you can convince. I don't agree that drones are so expensive. In my opinion, they can be quite cheaper compared to what you pay for a truck or for somebody who is driving the truck. I know that this is another topic, but I don't think that's so expensive. I think they can be applied, and we can see that they are applied. And so maybe you can bring some other example of other companies doing that to convince companies. But yeah, I agree on the other things you said about the fact that decision can be made on the spot. That's true. That's true as well. In this problem, we didn't take that into account. We just simplified the model because it was very hard to solve.
So maybe being changing the rendezvous location on the fly may simplifies the problem because you don't have to account for that wait time. So it depends on how
or maybe yes, of course, or maybe we can have, I don't know, like some hubs where we can have the return of the drone, and then the truck can go and recollect the truck in a later time, just not to have the synchronization. So yes, we can have several mixture version of this. Yeah, that's a possibility.
Stefano, I'm going to jump in with a question too. How does the number of instances and the endurance times that you've modeled here compare with what's going on in practice? Is it similar or is it still much smaller?
Well, it depends. So most of the times when you solve routing problem with the exact method, and particularly hard routing problem, maybe you would come to say, okay, that's not a typical number of customers that one company has. But then it might still be viable to have small customers that allow for have a drone delivery, for example. So in such a sense, it might be still realistic. But I'm sure that we need to solve way larger instances for sure to be more realistic, especially if you want to introduce more features like time-dependent travel time or stochastic information. Yeah.
Okay, so in view of the time, I'm going to stop the first part. So I want to thank Stefano again for introducing us to this very interesting problem with one of the latest technological development. And we can already see there are many, many different directions that we can improve and different aspects of this technology that we can model. So Sue already asked the question, and we look forward to more interesting developments from you on this and other interesting project. So if others have other questions, we will also have some time right at the very end if you want to bring up additional questions for Stefano at the end. Okay, so again, thank you, Stefano.
Thank you very much.
Yeah. So I want to move on to our second speaker. Our second talk is by Christian Leonardo Camacho Villon. So very complimentary. Stefano is from Italy, Europe, and has worked in South America. Our next speaker, Christian, is from Latin America and is now working and has his degree and is now working in Europe. So Christian is, let me just read his bio. Okay. Christian has a degree in computer science from, I'll just try to translate it, the Autónoma National University of Mexico, and a master's degree in information science and technology from the Universidad Autónoma Metropolitana. Okay, but then he got his PhD in engineering science and technology from the Free University of Brussels. He has been a postdoc, first at Iridia and in Brussels, and is now a Maria Slodowska Curie Fellow at Institute Josef Stefan in Slovenia. Okay, so both speakers have traveled many different places. Christian's research is in black box optimization, machine learning, as well as applications in optimization, machine learning, and automated algorithm design. I'm very interested in the topic where he will give a framework for looking at classifications of different meta heuristics. So the floor is yours, Christian. You have to unmute.
Yeah, sorry, it always happens. Can you guys hear me? Can you see my slides?
Yes.
All right, great. Thank you for first of all for the invitation, for the award. I'm very happy to be here, and yeah, I hope you enjoy this talk. It's not about one single problem, but mostly something that is happening in the field of optimization. So, well, I will start. So I'm going to talk to you about novel metaheuristics inspired by bestial metaphors. This is the topic of the paper that won the best paper award in the survey category. But before talking about that, I'm going to talk just to make this presentation self-contained. I will talk about optimization problems, the so-called metaphor-based design of metaheuristics. Then I will present some examples of these novel metaheuristics that are questionable in many ways. And finally, I will discuss some of the efforts that have been proposed by the community to address this foundational problem, I would say, in our field. Of course, I'm going to present some of our work regarding how we are trying to address this issue. And there will be some time for questions and answers as well. So maybe I'm preaching to the choir, but in any case, I would like to introduce optimization problems, which involve, finding solutions that are optimal or need optimal with respect to some goal. And to put this in a very intuitive way, is about finding the inputs that will result in the best outputs according to some criteria. You can have something similar to what Stefano presented just now, so about resource allocation problems. When you have a limited budget and you have competing objectives, and then you want to somehow fulfill as many as possible. You can have also, it's related to the previous talk as well, like shortest path problems, where you need to move from one point to another, and then you want to minimize the cost of the getting from that one point to the other, and then according to some metric can be the cost, the time, and so on. And another example is engineering design problems that involve, for instance, having a simulator, and then in the simulator you have a number of variables, and the values of these variables will determine how good or poor is the design. So in practice, we use many different types of optimization algorithms. And the problem is that in many cases, the problems are so difficult that we cannot really solve them efficiently with traditional algorithms. In this talk, I'm going to be referring to continuous optimization problems with one single objective. And in these problems, the goal is to minimize a dimensional continuous objective function. And the idea is to find this vector for which the objective function will return the minimum value. And there are many problems that can be formulated like this, and they are difficult to solve. So for instance, when you have multimodal non-differentiable functions, those cannot be really solved with a traditional method like a second derivative or something like this. Or you can have a black box, and this is the most common case probably nowadays, where you don't really have any information about how the objective function is structured, but you can still input some values to the black box, and then you will obtain a result. And in these cases, when we cannot really solve these problems in this efficient way with traditional or exact algorithms, we rely on method heuristics. And method heuristics are like the good enough shop. So if you don't really care that much about the optimality of the solutions, then method heuristics are an excellent option, with the caveat, of course, that they will not guarantee that the solution is optimal, although in many cases, they actually get to the optimal solution. And there are many aspects that make meta heuristics also particularly appealing. So the first one is that these good solutions are provided in a reasonable time. So you normally don't have to wait that much to get something that will fulfill your criteria. They are general. It means that you can take the same algorithm and then you can apply it for many different problems with very few or no modifications. And something that has been appealing for a large number of the people integrating or joining the field in the last 20 years, I would say, is the fact that some of these very successful method heuristics have been proposed based on different sources of inspiration, like natural evolution, the social behavior of some insects, the engineering of metals, and so on. So this is what we call the metaphor-based design of method heuristics. And initially, when people started to look at this process and realized that there was some optimization in the process itself, basically what they do was to take this observation of natural phenomena, and then they use the observation to find effective design choices that they could be translated into an optimization algorithm, such is the case of evolutionary computation, simulated annealing, and column optimization, and particle swarm optimization. And this created this popular misconception in the field that basically nature is a never-ending source of inspiration to solve optimization problems, which I'm pretty sure you will agree with me that is not true. But even more worrying is that now there seems to be a delusion, well, what I call a worrying delusion at least, is that now everything can be a source of inspiration to solve optimization problems. So maybe some of you are familiar with the evolutionary computation bestiary. So this is a website that is been compiling algorithms inspired by all kinds of metaphors. And you can see like from 2000, well, this is from 2005 to 2024. But there are some years where some people have been very active proposing new metaphor algorithms. So just for instance, 2000, 2014, we found more than 25, almost 30 different metaphors to develop optimization algorithms. If you go to the literature, you will find something like this. This is what we call, or we refer to as the metaphor rush. Basically, you have all kinds of metaphors that have been used to propose all kinds of optimization algorithms, ranging from African buffaloes, from frogs, monkeys, worms, intelligent water drops, gray wolves, and so on. So the problem is that if you look at these algorithms, it's really difficult to understand what is the motivation to use the algorithms. It's not clear what is the usefulness of the metaphor in the design choices that were proposed in the algorithm. And it's also not clear what is the novelty of the algorithms themselves. So when I look at this, or initially I was still doing my PhD, it seemed to me that many of these algorithms were just similar to particle form optimization, evolution strategies, or differential evolution. And I talked to my supervisors at the moment, Marco Dorigo and Tomasz Studle, and we started to analyze some of these algorithms, and this is what led to this paper that won the award. So in this case, in this paper, what we did was to look at 6 metaphor-based heuristics, and then we perform a component-based study of them. So our goal was really to understand what is proposed in these, why the proposed metaphors were being used to propose algorithms, and what were the novel ideas brought to the field of metaheuristics. And what we did is this component-based approach, where we extract their mathematical model, and then we compare them with established optimization algorithms, such as the ones that we already have some intuition that they were similar. So how does this study works? Okay, so first, the goal is to understand what are the ideas proposed in the metaheuristics, the way they are used to solve optimization problems, and we deconstruct the algorithms into these independent parts that they have, and we look at the role that they play to the performance of the algorithms. And these parts are often interchangeable, so it's easy to see that over time, people propose new ideas, and then these ideas are changing, are improving in order to get the optimization algorithms to work for broader classes of problems. So I'm going to give you an example. So particle form optimization is one of the algorithms I know best, and it's the observation that led to this algorithm is that by following simple rules, birds' flocks could display strong synchronization in the initiation of flight, or turning while they were flying, and landing. And in this case, the metaphor is used only to say, by abstracting these ideas into an algorithm, we consider like particles to represent solutions to the optimization problems. And the idea is that if you apply a velocity vector and to a position of the rule, then particles will move on the search space. So in order to perform a component-based study, what you have to do is to go to the past, to the beginning, to the first of these algorithms. You look for the different ideas that were proposed, and then we start studying the mathematical model. In the case of PSO, well, it's a simple vectorial system where you have an inertia, previous velocity, you have a personal component, and then you have a social component. By adding these 3 terms to the velocity or to the current position of the particle, you will provide the particle with movement, and then it will move to different parts of the search space. And then, of course, over time, people propose other ideas to provide movement to particles. And for instance, in this case, in the fully informed PSO that was proposed a few years after, the idea was instead of letting a particle be biased only by one social component, we can use all of the components in the neighborhood of the particle. Then the movement is going to be different. Or, for instance, in a simple dynamic PSO, they totally got rid of the idea of the velocity of the particle, and it's basically a mapping using a normal distribution between the best position found for the particle and the personal best, in the neighborhood of the particle and the personal best position of the particle. So there have been many ideas proposed to this algorithm. Another one is this, in which basically you compute the centroid according to 3 different positions, and so on. So what we did with PSO was to start to understanding all these ideas and to put them together in a framework, which I'm gonna present at the end of hopefully at the end of my presentation. You will see some examples of that. So in this paper, our intuition was, as I mentioned before, that these meteoristics were similar to novel meteoristics were similar to PSO. At least they were sharing some of the components, right? Okay, and just to make this a little bit more interactive, and probably just to give you something to laugh, hopefully at the end, I want you to think what is the result of crossing a wolf with a moth, right? Okay. Just probably later we can just short those to see if some of you have some ideas.
I think a tiny cat with wings.
Tiny cat. Okay, yeah, I have some thoughts. So you will see. You will be surprised, hopefully. All right. So in this paper, in the paper that we sent to ITOR, what we did was to take 6 of the most cited of these algorithms. So I was actually a bit appalled the other day when I saw how many more citations they got these papers. It's just crazy. So when when we submitted the paper to ITOR, the Gray Wolf optimization, Gray Wolf optimizer had about 11,000 citations. That was not long ago, and now it's 20,000 citations. So these are really highly cited papers. We analyzed the Gray Wolf optimizer, analyzed the moth flame optimization algorithm, the whale optimization algorithm, the Firefly algorithms for multimodal optimization, the BAT algorithm, and the antlion optimizer. I put here also the cuckoo search, which is a popular algorithm. We didn't put it in the paper. It's a different paper, but still we wanted to include it in just to give this an idea of how this problem is happening in the field. So this is the spoiler, but these 5 algorithms that you see here, like the first 5, well, we could match their algorithm components directly to components proposed in particle swarm optimization. I cannot provide an example of all of them. I mean, that's in the paper, but I think at least I will go to three examples of this so you can have an idea of what is happening. And then what we found is that this antlion optimizer and the cuckoo search algorithm, they are evolutionary strategies. So the components are there, they were proposed. And if you see, like, it's something that happened 20 years after the particle swarm optimization algorithm, the first variant was proposed. Well, somebody proposed the Gray Wolf optimizer, and it turns out to be something as old as 20 years before. Okay, so the Gray Wolf optimizer. So in this case, the source of inspiration is supposed to be the gray wolf, the way gray wolves organize for hunting following a strict social hierarchy. In this case, solutions are referred to as the pack of wolves. And if you have the 3 iteration-based solutions, these are the alpha, beta, and delta wolves. In this case, they are hunting, of course, something, which is the global optimum, but it's called the prey. So how does this algorithm work? Basically, you start by selecting these 3 best iteration-based solutions, and you will apply you will create this hypercube in which you're going to map a point. And that point you will map for each of these 3 solutions, and then you will use that point as radius around these 3 solutions. And then you will map another point within the radius, and then you will compute the centroid. So we found that basically all these ideas were proposed in PSO, not in one specific variant, but in different variants. And in particular, we found that it's, well, not have it here, but it's the standard PSO 2011 when you are computing the centroid. But the other components where you only adding a random vector in order to provide some diversity in the way the particles will move. Well, those ideas were already there. So our conclusion was, of course, that this algorithm is just a particular variant of PSO. And now, then we follow and we also analyze the moth algorithm. In this case, if you're looking for a source of inspiration, this sounds like the wrong source of inspiration because it's the useless or dead spiral flight path of moths around artificial lights. In this case, moths are the solutions. and the personal best solutions of the particles are the flames. And it works like this. So basically, each particle will keep a record of its personal best position, and then they will be ranked based on the quality of the solutions. And depending on the ranking, they will move from one personal best to another. It means that instead of using its personal best position, it might use the personal best position of a different particle in PSO terminology. So this basically creates some movement like this based on the position of the rule. And this is, of course, not how moths are flying around flames, right? So it's also in the paper. So the authors recognize that it should be noted that this assumption is done for designing the moth flame optimization algorithm, while possibly is not the actual behavior of moths in nature. So you may wonder, why are you using a metaphor from nature if you are at least at the end doing something else? And well, I'm not a biologist, but as far as I know, this is similar to thinking that moths are able to teleport, and I don't think this is possible. Anyway, so you have a field that is full now of ideas that are so far-fetched, where this is actually not the worst or the most incredible thing that you will see. And then probably the only contribution of this algorithm is computing the way you compute a parameter in the position of the rule. So then again, we found like the moth flame algorithm is also using concepts that were proposed for particle swarm optimization. And that was our conclusion. So, okay, now I would like to go back to this question of what happened when you are crossing a wolf with a moth. So if you thought of something like this, a furry friend, similar to what Gianni said, but yeah, well, you would be wrong, unfortunately. And then if you thought it would be a wolf with wings, well, that's also wrong, although it looks more interesting probably. And if for whatever reason you said that the product of crossing a wolf with a moth is a whale, you would be right. And not according to me, but according to the author of the whale optimization algorithm, which is also the author of the great wolf and the moth flame algorithm. So in the whale optimization algorithm is inspired arguably based on the bottleneck strategy that humpback whales use for hunting. And in this case, core solutions are called whales, and prey is the global optimum. So what the author of this paper did was just to take the mathematical model of the gray wolf, the mathematical model of the moth flames, and alternate between the update rules of the two algorithms. And there you go. You have a whale optimization algorithm. If you think this is nonsense, well, you are not alone. I think many of us have been thinking that for a few years. But then again, just by transitivity, well, the whale optimization algorithm is also particle swarm optimization. So now we have identified this foundational problem, like since a few years ago, and there's been some efforts to address this problem that we call the metaphor rush. So of course you have the foundational paper by Kenneth Sorensen, Meteoristics, the metaphor exposed, also published by ITOR. I think this is the paper that originated that at least some of the efforts that I conducted over the years were based on this foundational paper. You have some other papers where Dennis Wayland, he compared harmony search with evolutionary strategies, and he found something similar. He was probably the first one doing this component-based analysis where you go in the past and then you look for specific design choices proposed for the algorithm, and then you find whether there's a parallel between the two. And if you want to read something just sarcastic about this, well, I recommend this paper, A Spectral Approach to Ghost Detection. It's just sarcastic, but it's really fun. And sometimes when you read this, it sounds just incredible that actually some things that they were saying, like, yeah, why don't we propose an algorithm based on this far-fetched idea? Well, there are some like that already proposed. So if somebody's asking why is this such a big deal, well, there's been many negative consequences to this metaphor rush. So the first one is that there's a fragmentation of the field of meteoristics, because now it seems that we found more than 100 different novel ways to solve optimization problems. And for anyone who's reasonable, I think this is just not cannot be true. Then also there's been increasingly challenging to find or to draw comparisons between optimization algorithms, because now you have many different terminologies. And then what's a prey, what's a solution, what's a whale? All those things have started to create confusion, especially to newcomers to the field. And there's also what I mentioned before, but is this false idea that basically now if you have a new metaphor can become a new approach, and that new approach, in some cases, some people have gone as far as to say that it's a totally new field, which, well, doesn't seem reasonable. And finally, there's this problem that is creating a damage to the reputation of an external perception of the field of metaheuristics. So there's been some efforts trying to mitigate the metaphor rush. So some of what we have conducted ourselves is also like creating awareness. So publishing these type of papers where we discuss the problem and we mention the negative consequences of publishing these type of algorithms. There have been some papers who are trying to clarify what's really in these groups of metaphor-based algorithms, try to disentangle the metaphor from the components and so on. There's been some modeling frameworks, some taxonomies, and metaphor-free descriptions. And something that I found very compelling, at least, is that it's better when you provide them with an alternative, something that say, if you want to propose a new algorithm, why don't you do it in a more sound way? And this is what I will talk in the remainder of my presentation, which is about metaheuristic software frameworks plus automatic design. And another one, which is, I believe, is the strongest and the most effective way to deal with this, is to establish editorial policies where you say we are not going to publish this type of papers. So many journals have established these editorial policies. ITOR is one of them, but there's also some other journals, and this is helping. So what I have been discussing so far is the way metaheuristics can be designed manually. Now I want to talk about also automatic design of metaheuristics. And the problem is that when you are interested really in the high performance of metaheuristics, well, this is difficult, it can be time consuming, and it's prone to error. And in this case, high performance means that you want, for instance, better solution quality, you want the algorithms to run faster, and you want the algorithms to be applicable to different classes of problems, right? So traditionally, the way we have done it is just using basic ingredients. So experience, knowledge, and intuition, sometimes inspiration from natural behaviors. And this has resulted in some interesting metaphor-based metaheuristic with a sound scientific background. And the idea is to manually design each of the components, right? But as I mentioned before, so this can be very time consuming, it's prone to errors, and in general has some other limitations, like it's subjective and difficult to reproduce. So what we have been proposing also is to use automatic design. So instead of having a human doing this tedious task of taking the components, finding how to combine them in order to create the algorithm that is performing, you can delegate that to an automatic algorithm configuration tool. And in this case, the algorithm is not really just one single procedure, but you have an algorithm template where you can actually add and change the algorithm components in different ways. So a few years ago, what we did is to propose also a PSOX framework. It's a flexible modular framework for particle swarm optimization. And the motivation to propose this is that many of the algorithms that we already studied were basically variants of particle swarm optimization. So in this case, we put all the components across 25 years of research into a single framework where you have many different ways to initialize the solutions, the topologies that are used, the concepts that are used in particle swarm optimization. And what we did is to propose an algorithm template. In this algorithm template, you can take all these concepts and then you can add like a plug and play, and then you can change them. And by changing them, basically you will be producing novel implementations of PSO, but also you are able to replicate the implementations that already exist and were proposed before. So this allows you not only to propose new ones, but also to compare with established algorithms. And so we did some experiments with this. So what we used in this case was an algorithm configuration tool called IRACE that was proposed in 2000, well, published in 2016, where you have this paper, but the tool was available before. And this tool requires three things. So a set of training instances, which are going to give you, like, give Iris some parameter, like training space or some data set in which to train the algorithms. Then you will have, in this case, different types of problems. So we include unimodal problems with one local optima, multimodal problems where you have many local optima, hybrid functions where you have something more complicated, like different parts of functions belong to different functions defined in different way, and function compositions as well. So these are normally difficult problems to solve, so they are good to train something that is general, right? And the parameter space is the framework where you have all these components, and we use different scenarios. So it means that you give different budgets to the automatic algorithm configuration tool, depending on what's your budget, of course, but also in this case, we said, like, if we're going to give the framework with the 48 parameters, we will use a larger budget than when we are just comparing with or tuning, trying to fine tune PSO variants that were already proposed in the literature. And what we found is that basically by combining components in different ways already proposed for PSO, you can create variants that are more performing than other ones that were like even the state of the art. So we created six novel implementations, and we compare against default and tuned variants of PSO. And well, not surprisingly, we obtained better results. And these are some of you just see me here as a box plot. So these are minimization problems. So the lower, the better. And this is something that we found even for the more difficult problems. And we use 50 and 100 dimensions because these were, like in our case, related to the maximum number of dimensions that you could have in the benchmark set. Something interesting, and this is something I would like to discuss just for a minute, is that this one in blue is the standard PSO. It's the first variant of PSO proposed in 1995. But we found that just by tuning the algorithm based on the benchmark, you can actually obtain much better results. And it's interesting because some of these papers where they propose these novel metaphor-based heuristics, they are not doing this any tuning of the algorithms. They are comparing against default variants of the algorithm. And then when you compare with the default, well, the results are normally worse because they were, like, the default parameters were set for other types of problems many years ago. So just by doing some parameter tuning, you can actually improve the results of the algorithms. But we have been trying to take this idea further. So as you saw in the analysis of the algorithms, so some of them were similar to PSO, but some others include components from evolutionary strategies or other meta-heuristics proposed also many years ago. And then what we come up with this idea of creating hybrid meta-heuristics, where you can actually combine the components not only of particle form optimization, but also some other approaches. In our case, we are considering evolutionary strategies and differential evolution. So we have this framework. This is something that is going to be published soon, but it includes 105 components from state-of-the-art meta-heuristics for continuous optimization problems, such as CMAES, differential evolution, and particle form optimization. And we created, in this case, even more algorithms combining all these components. And we use an extensive number of problems with way larger dimensionality, up to 1,000. And we found that you can actually use this approach to find something that is even better. You have more flexibility. You increase the complexity, of course, of creating the algorithm, but you have way more flexibility in the type of algorithms that you will produce. And it's a sound approach in order to produce something that is both novel and high performing. And well, these are some of the results that we found. In this case, for instance, you have on the left side, you have variance of particle frame optimization, and on the left side, sorry, on the right side, you have variance that we created using this framework that allows to combine not only PSO, but differential evolution and so on. And we keep observing that the results can be greatly improved. So I want to conclude my talk just now, just to tell you that, well, in our paper, we address the problem of the novel metaphor-based meteoristics. The problem, unfortunately, is still ongoing. If you go to the literature, you will find still many of these algorithms proposed in the last years. I would say that the main contribution of our paper is to provide further evidence that the metaphor rush and the hundred of these algorithms have a negative effect in the field, that they lack novelty, and they are in many ways just noise in our field. And the last thing is that we advocate for the use of automatic design. It means that we rather have some of these frameworks where you can combine the components in different ways, and you use an automatic algorithm configuration tool to do so. And this allows to design truly novel algorithms with high performance. All right, and with that, I conclude. Thank you.
Thank you very much. Thank you, Christian. So I know, I think Mark Savol was here earlier. I don't know if he's still there. You have further comments. I know there's been a number of researchers that have been very concerned about this explosion of this meta-heuristic zoo that that have developed. So I think it's really wonderful that your analysis of this whole field and comparison of the different things. So I think I feel very gratified to hear of your work, because I think it once again show that deep, careful analysis is much better than the fuzzy metaphors that we have seen in many of these papers. So I really think it's I really think we should summarize, your work and hand it out to all the editors of all the journals. So the next time they see one of these papers coming in, they have a good framework to measure, the novelty of these supposedly biologically inspired algorithms that we see in many of the submissions. So thank you very much, for a very interesting and entertaining talk. Are there any questions? Or maybe I start off with one. So I like this final overall framework that you have for developing meta-heuristics, So but I guess in some ways I worry if this final framework is so perfect, then we have no room for others to be more creative about meta-heuristics. Is there, some aspects that you think maybe the particle swarm doesn't have that we could incorporate in this, extend and enrich this framework that you have?
Yeah, I think so. I think this is far from being final, like very far. I can say two things. So the first one, I believe there's still room for people proposing new components. This is just the way you are doing it. I'm pretty sure even when I'm like creating some these preliminary designs for the algorithms, I found that many ways, a new component could be added here where you have something with this or that characteristic. So I strongly believe that there's no, this is not really the end for this framework. The other thing is that, in my opinion, in the future, we will have something that is much more efficient now that we have large language models, and then we can use some really more like effective ways to actually sample these algorithms from a framework like this. So what we did with IRACE and this automatic design approach is really taking all these, and by applying some heuristics, actually, you try to identify where are good algorithm designs. But I'm sure that if we could exploit all the knowledge that is already in many papers where people have done like very interesting and very sound experimental studies, we can actually create better designs faster, and even to come up with new components in a more automated way. I think this is just pretty much not, but for our field, not the beginning, but it's really, there's a point of inflection where we're gonna be seeing something that are just much more carefully created, and they are more also general, because you can train these type of models to actually give people in the community ways to, for instance, you have something like this, you can actually give something to editors, something like this, and say like, maybe you can query the LLM, and the LLM can tell you an idea of whether the components in this algorithm are novel or not. So I think this is really, there's many things still to it.
Good. So it's good that we have, more interesting directions that we can try to extend and enrich this framework. I like your idea you bring up. So one side is to build an enriched framework, and the other side is, using maybe large language models to have an effective way of evaluating and assessing these meta heuristics. That's very nice. Yeah.
Yes.
Where does this framework fit in with the practitioner community, the people who are solving optimization problems on real world problems?
Yeah, that's a very interesting question, because it's a question actually I get often. Like, is this just purely academic, or can you use it for solve real world problems? And the answer is yes, you can use it for solve real world problems. So you can, of course, include your problem within the framework, and then to follow the approach, the automatic algorithm design approach, to get an algorithm that is tailored for the problem. But another thing that you can do is just take one of the algorithm designs that we already have, and you use the framework to solve it without having to do anything else. You just apply that. And because the result of using automatic algorithm design is that you will always start from something that is really good. You don't have to go to find a new metaphor or something like this. You just start with this one, and then you can apply it. But it's the two approaches are possible. You can still try to improve over something that we are already giving you that is good, or you can use it, and then if it's not good enough, then try to find an alternative.
Okay, so I see Marcus has spoken up, and I don't know if everybody can see his comment, but I'll just read it out. Maximo says, it's a pity that many of the creators of these nature-inspired methods are probably just trying to increase their H-index and number of publications. And it just adds many confusion to the meta-heuristic community. So he thanks you, Christian, for the presentation and this automatic design of meta-heuristics. And I join him in that comment as well. Okay, so I guess in view of the time, since we don't have any more questions, we'll try to wrap up this global webinar. So I think once again, I thank both speakers and all the participants who have joined in. I think just with two speakers, we seem to have covered geographic coverage of across the world, and in terms of topic, coverage from optimization models to meta heuristics. I think what makes our operations research field is so exciting is that in all the problems we address, we have to balance so many things. The realism of the problems we are trying to study, the sort of the closeness to optimality of the solutions we are trying to bruise, and the efficiency in time efficiency of the algorithms we've developed. So this balance of how much realism we model, how close to optimality do we require our solution methods, and when do we switch over when we scale up the problem to go to meta heuristics? It's a very interesting question that we all have to balance. But I think both the talks today sort of really highlight good, detailed, careful analysis is what brings insight to what we study. So again, I thank both speakers very much. Well deserved your best paper awards. And we hope
Gianni, we've got one more question popped up.
One more question.
Don't know whether you want to wrap up with that one.
Okay. All right. So the question is to Christian, can the automatic design of meta heuristics be applicable to discrete problems? Can it be modification or extension of your method? I'll let you answer it.
The answer is yes, of course it is applicable, and there's already some works on that. I can tell you, for instance, about one framework that it's the result of the work of Manuel López Ibáñez and Tomás Tutle. It's Moaco frameworks for multi-objective optimization with uncollinear optimization, and it's for the, I think they tested on the multi-objective TSP. So there's many methodologies. So this is something. This is one example that I'm giving you, which is based on my work and continuous optimization problems, which is my main research field. But this methodology was proposed before, initially for discrete optimization. So yes, there's many options. And if you go to the literature, you will find like this framework. Some of them, or most of them, I think, are available. So anyone can take them, use them, and solve the problems. So yes.
Okay, all right, that's a great answer. So again, I thank both speakers and all participants in this global webinar. So be sure to stay tuned to our website and our LinkedIn page, where we will announce future webinars and other events of IFORS very soon. So thank you all for participating again.